This is Wednesday, April 8th. Also, quiz 9 is due. This is the NMR quiz, and it's that 4-page monster. Sorry about that. So make sure you print off all 4 pages. That last problem is a tricky one. It's a harder problem. You really have to examine all the pieces of data, including the C13, along with the proton NMR, and the mass spec and the IR. If you put it all together and look at the pieces and kind of approach it that way, you'll arrive at a good structure. I'll give you a little hint there. On problem 3, quiz 9, you'll notice there's a 3-to-1 ratio of isotopes for a specific halogen that's involved there. And 3-to-1, that should tell you which halogen's probably involved. So you want to adjust your molecular weight there and then figure out your molecular formula, the ratio of atoms from that. But make sure you examine all the pieces of data. Test 4 over chapters 12 through 15 will start next Monday and Tuesday. We'll have that up sometime on Monday. I don't know. Look for it in the file on Learning Suite. It should be okay there. Anyway, so that's the information there. Before I go through the details of chapter 15, the outline, it is radical chemistry. You might be thinking, well, what are some of the applications or what's the importance of this? To catch your attention here, I point out a historical molecule, this triphenyl bromomethane molecule. And if it's reacted with metallic silver, you form silver bromide plus something that's stable here. It's got carbon-19 H15, which is an unusual molecular formula. There's no nitrogen in here, but what? It is an odd mass. And this puzzled chemists for a long time. What is the structure when this bromide reacts with silver? Is it this molecule here? And what was proposed early on was this. Phenyl stands for the benzenes, right? And that stays intact, but what's on the carbon now? Well, just an electron. And chemists really scratched their head over this because it was known at the time, of course, that carbon was what? Tetravalent. It has 4 bonds and what? 8 total electrons around it for the octet rule. But here we have a molecule that what? This carbon right here has 3 bonds and 1 electron. So that's 7 electrons? Question mark? Well, that should be unstable. It should react and give something else. But now you can actually make this molecule and it will persist. It will stick around for a long time, even though it's coordinated and saturated and has an odd number of electrons. We say it's a persistent radical because it's sterics, which makes it a different type of radical, and it's also highly stabilized due to resonance. So it's really 2 things that help make this molecule, even though it's very unusual, very stable, but indeed it is mass spec 243 with no nitrogens. And it is this odd electron species here. A lot more I could say about that. It was discovered by Moses Gomberg at the University of Michigan in the early 1900s and really puzzled chemists for a long time. The theory and the characterization of the molecule really took a long time to figure out. And it kind of opened up this radical chemistry that we're talking about. Now, there's something you're probably more familiar with, dental onlays. Hopefully you're not too familiar. But all of us have to go to the dentist periodically and have cavities filled, right? They drill out the hole, and then they put in some stuff. They might have to put a crown or some other onlay material there. But the adhesive material is this, a acrylate ester, a double bond conjugated to an ester here. It's in a matrix of other things, some silicon oxide and some other materials that are just vehicles for the adhesion process. What actually forms here when the dentist shines that blue light, once they get everything on there, you've seen the big blue light gun, and maybe you've asked about that. Well, what's up with that blue light? Well, it's initiating the polymerization process. The actual initiator in this case is this camphor diketone that, in the presence of blue light, undergoes an excitation and forms an oxygen diradical intermediate in the excited state. That initiates the polymerization process. And what you get is a polymer, carbon backbone here with a lot of carbons in the chain, and each one has the ester, and it alternates here. The methyl group and the ester here from the acrylate will alternate. And we'll get into the details of what this is, but there can be hundreds or thousands of the length long here. This is a solid material, of course, and your teeth and the onlay are porous. So this material fills in those holes, and this covalent polymerization affixes those things very tightly, fortunately. So we'll finally let you know what the dentist's blue light's all about there when we get to the polymerization part. But let's look at the outline for the chapter here. We do have a couple new reactions, not many. The reactions that we cover in this chapter are similar to the ones we've covered already, but the mechanism and the reagents and the basis for how they work are different. Okay, when we're talking about radicals, we're talking about odd electron species, 7 electron species that are different from the electron paired species. And we're going to be involving homolysis of bonds to initiate and start these reactions. That is, we're going to be forming radicals. Instead of doing heterolysis, where we've always kept the electrons paired with cations and anions and species like that, the electrons are always coupled. But now in radical chemistry, they'll be uncoupled. We'll talk about radicals in general, 7 electron species, sp2 hybridization. For the intermediate radicals, that can either be allylic, tertiary, secondary, primary. So that should be familiar. That parallels carbocation concepts we've been talking about. But the mechanism will involve radicals and a chain reaction mechanism. So this will be different. There'll be an initiation step, which will shunt the process into a radical pathway, and then there'll be propagation steps that'll consume the starting materials and form the products. And this is fundamentally different from our anionic, cationic reactions we've been doing previously, SN2, SN1, E2, E1, and all that. We'll have 4 new reactions, and let me specify them clearly here in the outline. We'll have alkane halogenation, and these are alkane. These are saturated hydrocarbons, okay? No double bonds here. So this is kind of a different thing. We told you that, carbon-hydrogen bonds, is that a functional group? If it's sp3 hybridized in alkane? And I warned you, yes it is. The book may have said, no, that's just the carbon framer. But now we're going to be doing reactions with hydrocarbons, okay? So those sp3 carbon-hydrogen bonds can be reacted with halogens. Chlorine and bromine, we'll stick with that. Fluorine's too explosive, iodine's too unreactive. The practical ones are chlorine and bromine. And we're going to form alkyl bromides and alkyl chlorides, okay? So the reaction, keeping track of the atoms, is pretty straightforward, similar to what we've seen before, but we've not reacted alkanes before. This is the first reaction. No, we did combustion, that's right. So this is our second reaction with alkanes, burning them, of course, to CO2 and water, but now we're forming the halogens. And the mechanism, like I said, will involve abstraction, initiation, and propagation steps, so we'll get into the details of that. We'll look at the bond dissociation energies and the relative rates and the selectivity. Chlorination is not very selective, okay? These are the relative rates at the tertiary, secondary, and primary positions. It's 5 times faster at tertiary, 3.8 times faster at secondary relative to primary substitution. And that's a reflection of the stability of the radicals, but it's also a function of how exothermic the steps are for propagation. So it's not very selective for chlorination. But bromination does give higher selectivity, over 1,000 to 1 and 80 to 1 for tertiary and secondary over primary. And that's because the individual steps are endothermic. So by Hammond's postulate, those transition states can be differentiated better, and you get higher selectivity with bromination. So bromination, if you want to selectively halogenate your hydrocarbon, you'd use that reagent. And we'll review a little bit of synthesis, why this is important. Well, once you have an alkyl halide, you can do all your SN2 reactions, you can do your eliminations, and make a lot of different materials. Stereochemistry, these are achiral reagents. If you form a stereocenter, the radical is planar, and you'll see that when you form the carbon halogen bond, you can either form it from the top or the bottom and give a mixture of products. So those are the first, the first reaction. The second reaction is allylic halogenation, where we have an alkene now. So before we just talked about alkanes. And if we have our old friend NBS, N-bromosuccinimide, and we start it with light or peroxide initiation, we can get the allylic bromide product. And this is limited to bromides. So NBS, yeah, the bromines there. You can also do it with bromine, Br2, and we'll talk about the details of that. This allylic halogenation has to do with allylic oxidation using oxygen, called autooxidation, gives allylic peroxides from naturally occurring unsaturated fats. Both the mono and the polyunsaturated fats go rancid via this radical process with oxygen. Oxygen is also a radical. It can be an initiator. It normally takes time, but if you expose unsaturated fats, they will go bad over time. Antioxidants that can eliminate that pathway. In fact, you've probably heard of antioxidants or free radicals in the body, biological systems. Yeah, they do cause damage. They're naturally occurring free radical inhibitors, we call them. Vitamin C and vitamin E are both radical inhibitors in the body, and they trap damaging carbon radicals. So do a little application stuff of that. We can also add HBr to alkenes, and that's the reaction we've seen before, just that right there. But the new conditions now involve peroxide initiation, and we're going to switch. Instead of having the Markovnikov product, we expect the bromine at the secondary spot here. If we're under radical conditions, we get anti-Markovnikov reaction here, and we get the less substituted bromide now. So this is a complementary reaction with the reaction in chapter 8. So hydrobromination can reverse the regioselectivity to the less substituted one. So I think that's reaction 3. It's similar to what we've seen before, okay? And then if we leave out any of the other reagents here and just initiate a radical reaction with just an alkene here, we can get polymerization, okay? This is showing polyethylene right here, okay? And we'll look at some different polymers. So this is ethylene gas in the presence of a peroxide initiator. There's no other reagent here. So we'll initiate the radical, and that can add to more alkenes, and it can just polymerize and form a long chain. So let me show you some of these materials. When you're familiar with these materials, our world is surrounded, filled with different synthetic polymer materials, mainly from alkenes. Let's see, this first one is polyethylene, this cap to my water bottle here. And it's kind of a soft material. Let's add some dye here material. It's normally clear, so they add some other materials to it. But that's polyethylene being polymerized into low density polyethylene. You can make high density and weave it into fibers and all sorts of other types of materials. But PE or polyethylene is a very useful modern polymeric material. And this next one here is polystyrene. John Huntsman, the famous Mormon industrialist, made his millions off polystyrene, polystyrene foam for packing materials and whatever. This is a solid block, a prism of polystyrene. It's very hard material, but it's got characteristics that are quite different from the softer polyethylene. Then we have polyacrylate, which is similar to the dental onlay here. This is called an acrylate ester, and this is a little harder, a little bit different material. It's got a blue dye in it, but it's molded, you know, it can be formed into different things. That's the neat thing about these polymers. Once you form a solid block of the material, you can melt it back down and extrude it or mold it into whatever material you want. So there's a lot of cool things there in polymers. And these are just alkene polymers. There's a number of other polymers that we have, like nylon and polyesters and other things that we're not covering in this chapter. But let's go to the board here and start in on the material, what we need to cover and see here. So radicals, what we mean by these, sorry guys.
No, you're good.
They can move around a little bit. So let's cover the basics first. Let me go through the fundamentals of the structures of radicals, and we'll talk about the relative stabilities here. So just like we saw in Moses Gomberg's radical there, here's a generic radical carbon with how many electrons around it? Well, 2 in each bond, right? So we got 6 there, and then the 1 here on the carbon. So that is indeed 7 electrons, okay? Do we count this electron as a group? And what is the hybridization of that? Well, we've got a carbon with 3 ligands. So let's kind of look at it on the side here. And the radical, you could say, well, that's a half empty or a half filled p atomic orbital, right? So it's kind of the same hybridization as what? The carbocation, where we had an empty p orbital. So 1 electron's not enough really to push these other 3 down and have it be sp, what, 3 hybridized or trigonal, or sorry, tetrahedral. It's more trigonal planar. It's flat in that case. Well, where do these come from? Let's look at bond reactivity next. So what we've been talking about before in reactivity is moving 2 electrons out, right, and forming an anion and a cation. So that was like the first step in what, SN1 reaction or E1 reaction, where we ionize off a leaving group, which would be B here, with both electrons, double arrow, coming out in a heterolytic process where we get 2 different charged species, a cation and an anion, by the mutual motion of both electrons. But now in radical chemistry, we're going to be doing this. So single fishhooks, we're going to create 2 similar species, or homolytic species, where we'll have A as a radical plus B as a radical. And there's a lot of species that are known for this. Normally, to get this to go, we're going to have to heat this up or shine light on it. So it's a different process in this, where maybe we just put this in a polar solvent before. Okay? So here we're going to be doing something different, or we're going to add an initiator. Okay? And that initiator we'll see often in the reactions we're going to talk about. Let's look at the relative stabilities here. So if we have a primary radical, we're going to have that. So maybe one other thing. Oh, we also have a methyl radical. I'm not going to put that on there. But that's not very stable, and we need to remind ourselves why that is. An empty orbital like that, and if it just has 1 other carbon on it. There are other sigma bonds over here that by hyperconjugation can help stabilize this half-empty orbital. Okay? And then a secondary radical would look like that. It's more stable because there's 2 alkyl groups stabilizing that, and a tertiary radical is the most stable one. Okay? And we've also got allylic radicals, which are also very stable due to resonance. Okay? So you can imagine here, empty p orbital here, 2 p orbitals for the pi bond, and of course we could easily resonate these together, right? Put the pi bond over here and then a radical over there. Okay? So the true species looks like that, right? Where you don't have an empty orbital localized here and an empty orbital here. It's actually delocalized over the entire thing. So that's the same depiction with the resonance effect there. One other thing to point out here, comparing radicals to cations. So you could say, well, is the orbital half empty or half full? So it depends on whether you're an optimist or a pessimist or not, right? And there's one key reaction here compared to carbocations. It kind of gives it away. So let's say we've got this type of a radical here. It's a primary radical, and we've got branching nearby. Okay? And let's compare that to a carbocation that we saw before, right? This is primary. This would what? Undergo the shift right away, with both electrons coming out of this carbon hydrogen bond and then moving that over here to go what? To the tertiary carbocation. And these shifts, especially 1-2 shifts, either hydride or alkyl, happen very easily, okay? That's because we have an empty orbital here, and we just are accentuating the hyperconjugation, right? we're just bringing these electrons over and doing a reaction, shifting it from the primary to the tertiary position. This readily occurs. We've seen that many times with carbocations. But what about a radical here? What's the difference? Well, can we move these two electrons over here? Now, you need to remind yourself of something. How many electrons can we put in one atomic orbital? The answer is 2 by the Pauli exclusion principle, right? We can only put 2 electrons spin paired in a given orbital. Here we have an empty orbital, and we're just moving the 2 electrons over. So we're never exceeding that capacity. But what do we see here? 2 electrons, 1 electron's already there. So is it half full or half empty? Well, if you're an optimist, I'd call it half full, because it does have different properties than the carbocation. Can it occur? Well, some rare shifts are known with radicals, but the problem is you've got the sigma bond here, and you've got the sigma star right here. So let me give you a little more MO theory here. And in order for this to go, this radical would have to come over and fill into the sigma star. Now, geometry-wise, that's impossible to do. And look at the carbocation shift. This pi bond, or the empty p atomic orbital is right there sideways to that, and you're just filling in the 2 electrons. So that's allowed, okay, theoretically. But here, you can't put 3 electrons simultaneously in a bond. So this radical, if it were to rearrange, would have to go on the back side of this sigma bond, and that geometry is just not allowed. So we generally don't see shifts. Which kind of says that the radical is what? Half full, I would say, just reactivity-wise. But geometry-wise, it's flat like a carbocation, and the stability follows the same things we've learned about carbocations. All right, let's look at reactions in general now. So the reactions, you already have a little bit of a feel for this. The reactions are a little bit different. They're going to be homolytic with different types of things. And in the reactions, we're going to have to use heat or light to get these reactions started, or an initiator. And an initiator typically would be something like a peroxide. And we've seen peracids before, and we've seen hydrogen peroxide in general chemistry, and we've mentioned peroxide. This is not a pair of old-time glasses, okay? This is peroxide here with 2 tert butyl groups on it. This is a typical initiator for radical chemistry. And when we heat that up, you see this bond right here, if you add energy to it, it starts to oscillate, right? You can make that bond length compress and elongate, and if you add enough energy, eventually it pulls apart, okay? So let's see, how would it pull apart? Well, 1 electron would go with 1 oxygen, 1 with the other. And we'd create 2 oxygen radicals. So there are 2 lone pairs already on there. Here's the new electron from the breaking of that sigma bond. So how many electrons? 1, 2, 3, 4, 5, 6, 7. Same 7 electron arrangement. There's 2 of them, okay? So there's one initiation type thing there. Well, let's see, in general, how do radicals react? And I'm just going to stick with a generic X atom here that's a radical, okay? So it could be a halogen we'll see coming up, and other things, but let's just say X, keep it general right now. You can react that with a molecule that has a carbon-hydrogen bond, and how would this react? Well, it would react in this way. So we call it abstract a hydrogen atom. You can take 1 electron out of that hydrogen. It can hit the back of that sigma star. That's the geometry of it, but it's an intermolecular event, right? This is 1 molecule, this is another molecule. And if it does that, you see, the radical is now quenched. It's now an 8 electron species. But you see the carbon now is what? The radical, okay? And that's often seen in radical reactions. We go from one radical to another radical. You'll see that in the initiation and the propagation steps. Another thing we can do here is we can react like we already saw for the polymerization process. The fundamental step is adding to the pi bond here, okay? one of the electrons comes out of the pi bond, the other electron goes on the other carbon there. And so, yeah, these fishhook single barbs mean the motion of one electron, right? Now we make a carbon halogen bond and a new carbon radical right there. So that's another way to do reactions. Let's see, we can also do it if we have an allylic hydrogen. Instead of just adding to the alkene like that, we'll see with NBS and light and bromine with light that under those conditions, a bromine radical can actually, instead of adding to the alkene, we'll see how hydrobromination, okay, the anti-Markovnikov step. But there we have HBr. We have an active hydrogen atom we can transfer to the carbon. So that'll be a different process, and hopefully we'll keep those two distinct there and straight. But if we do this reaction here, you see we can generate HX, whatever it is, and then plus what? What results here? Oh, the allylic radical we just talked about, okay? So we've got a couple different things. Hydrogen atom abstraction, pi bond addition. Well, this is hydrogen atom abstraction too, but it's a little bit different because we get this resultant radical that's stabilized in that way. Okay, there are a couple other reactions we should point out to you. What if two radicals collide with each other? Can it go right back to the material? Yes, it can. However, radicals are unstable materials. They're high energy, and they're typically the concentration. Let's see the concentration here. In the brackets means molarity. Typically, this molarity is very, very low. So the probability of two high energy unstable radicals colliding with each other is very low, so this would be a very slow type of a step. But this will be a termination step when we make the polymers, so that is okay in that way. Yeah, I think that's all we need to say for the fundamental reactions there. We'll see some other things when we talk about oxygen here in a bit. All right, let's look at halogenation and get into this reaction here. And yeah, move over here, Isaac. We'll be using the overheads here in a second. So let's look at halogenation. And this is alkane halogenation. So alkanes with halogen, okay? So let's look at our first one, a simple one. Methane, okay? Heat that up with chlorine. Okay. Chlorine, very reactive material. You have to be careful of that stuff. If you heat this up or shine light on it, and this delta symbol is heat, right? So we often use that instead of specifying an exact temperature. But yeah, as long as we get this 80 to 100 degrees or so, this thing will go. Or shining light on it, and it really is the ultraviolet light that begins to excite chlorine. We'll get into the mechanism in a second. Let's just look at the products first. So we can form chloromethane, okay? And let's see, we also form HCl. The reaction does get acidic, so hydrochloric acid is formed. Normally it's easily neutralized with sodium hydroxide or an amine base, so you can get to that. Now the problem is here, if you're heating this up, or even with light in chlorine, you'll often get over halogenation. So you'll also get this. You'll get dichloromethane or methylene chloride, and that's not the end. You'll also get, what's this? Yep, chloroform, trichloromethane. And is that the end of the story? No. You'll also get carbon tetrachloride. That is the end of the story. You can't put a fifth chlorine on it. A lot of times industrially, all of these are commodity chemicals. They can make money selling these, whatever. This comes from natural gas, so or it can be made from synthesis gas, from hydrogen gas and CO2. There are ways to make hydrocarbons synthetically. We're not limited to petroleum for alkanes. But chlorination, you see, makes all these compounds here, especially with heat. We often get, well, let's say we always get poly products there, especially with chlorine. If you were the light and you do it at room temperature, you'll often just get the mono product. okay? And that would just be this one in this case, okay? So the over-halogenation, even if you try to control the amount of chlorine, the radical intermediates, as they get more substituted, are actually more stabilized, and it'll actually facilitate making more of the material. But let's compare this with bromine. Now bromine, we can also, have excess here and heat it up. But let's look at bromine and light. Okay. You can easily stop and get a 93% yield of the monobromocyclohexane, okay, which synthetically is a very useful process. Be able to selectively put on a bromide, which is now a good leaving group, right? So we can convert that to a lot of other things. Let's get a couple other reactions up here. How about chlorine, and let's say light and room temperature. So we're trying to limit ourselves to just monochlorination here. But notice, methane and cyclohexane, all the carbon-hydrogen bonds are the same, but not so with simple old propane, right? We've got a primary position and a secondary position. So what do you think here? Yeah, it'll be a mixture of things. And what type of ratio will we expect to get? Well, you may be thinking already about the mechanism. If we're going to form a primary radical intermediate, we might get less of this because the primary position is less stable. Secondary might get a little more, but we'll give you the numbers here in a minute and show you what we're looking at. Let's look at a couple other examples. One that's a little more complicated, of course. How about this? 2-methylbutane. And let's do chlorine. And just light, H nu, that's the symbol for light, right? A photon. H is Planck's constant, nu is the frequency, right? And you can change that. Usually it's the light in the ultraviolet region that does this most efficiently. But a lot of times it's just shining white light, intense white light, and the solution will get this to go. If you leave out this light, guess what? You get no reaction. Okay? Room temperature won't do anything. You gotta shine light on it. So room temperature light with chlorine will go. And what do we get? There's 4 different isomers. Let's see if we can figure them out. They're all monochlorinated things. So if we chlorinate here, that would be 1. So what would that look like? That guy. We could chlorinate at the secondary spot. We can chlorinate at the tertiary spot. And I think the only other one is out on one of the methyls. And the 2 methyls are the same, right? Due to the symmetry here. So I think it's only 4 products. Double check that. See if you can come up with another product. No, I think that's it. So those would be the ones there. But with chlorination, it's not selective. You get a lot of different products here. Now let's look at the details of the mechanism and see what we need to do here. Well, we're going to have an initiation step, and we're going to have a couple of propagation steps. So let's look at this one, chlorinating ethane. We're going to go to this. Okay. Yeah, chloroethane. Okay. And you can easily do that reaction with light. You do it just for a limited amount of time, or light, like I said, at room temperature, and then you'll probably favor monochlorination in this case. So first step. The chlorine-chlorine bond has to break. We call this the initiation step. Okay? So it's going to be a couple of different steps here on the mechanism, like I warned you. So the weakest bond here in this system is the chlorine-chlorine bond. It's is only about 58 kcals per mole. So when that starts to oscillate, eventually enough energy is added, you can break that bond homolytically, we say. And our first step here is 2 chlorine radicals, okay? And like I said, how much energy is that? Well, it's plus 58 kcals, okay? But it's just the initiation step. Now we've got radicals, and our radical pathway can now be followed with the propagation steps. And by propagation, we mean its radical is going to keep going until it's consuming the starting material. So here's our chlorine radical that we just formed. let's go ahead and abstract that hydrogen atom. And our next step is this, ethyl radical plus HCl. Okay. So at least we formed one of the products. That's what our mechanism has to account for. Now we're doing homolytical steps, so we've got this single Fisher craziness here. And we've got some different steps here in this chain reaction, it's called. We'll see why we call it a chain here. Let's see the next step. The ethyl radical now can what? React with chlorine. So there's more of the starting material, the chlorine. This board can't come up, Isaac. You double check that you're able to see this.
Yeah, I can see it.
It's okay. Okay, let's see here. So what would this do? Well, we can abstract this chlorine atom out of that. And keep track of all the electrons if you need to there. There's 2 in that chlorine-chlorine bond. So yeah, that gets to the product, doesn't it? So we have the ethyl chloride plus what? What's the byproduct of this propagation step? Look, it's more chlorine. Chlorine radical, elemental chlorine. And so there it is. Look, that just go back, that chloride, to this first propagation step. We've got 1 and 2 propagation steps. So this will just keep going as a chain, right? This reaction, these products here, this intermediate then is the starting material for this reaction. And this regenerates what? The product, of course, and it regenerates that chlorine radical. Okay, so the chlorine radical is called the chain carrier for this process. But you see that can just go until it eventually runs down. Now what about the energies here? Well, this is plus 98 kcals, the carbon-hydrogen primary bond, and our chlorine-carbon bond, like we said, is plus 58. So let's get a feel for the energies here. Our HCl, what's the energy there? Well, it's going to be minus, because that's being formed, 103 kcals. And then what's the other one we need to keep track of? Oh yeah, carbon-chlorine bond. What's that? Oh, that's worth minus 81. So what's the total energy here from the bond dissociation energies? It comes out to minus 28 kcals. So that's quite, what? Exothermic. Okay. So let's look up on the figures here from your book and see a little bit about this. So we've got, oh, that's that first reaction, methane being halogenated. And you can see, oh, I include the properties here. So these are the boiling points. Yeah, this one's a gas. These are all liquids here. You can easily distill all of these apart. So a lot of times in industry, they'll just over-halogenate these simpler hydrocarbons and then purify those by distillation and sell all of them. So it's not necessarily bad to have an unselective reaction if you're set up to handle it on large scale there. But yeah, so you can replace all 4 of the hydrogens in methane there. Let's look at the one we were talking about here. Oh, ethane, yeah. So here we got our initiation step. We just talked about, and a little discussion there of what it is. Sorry about the kilojoules. That's in kcals, so that's plus 58 kilocalories per mole. Then we got the 2 propagation steps, the chlorine radical from the initiation. And this only happens, the initiation, remember, is just that. It only has to be a little bit initiated. And once that chlorine radical is present in the presence of the reagents here, it just propagates. And then there's more chlorine, more Cl2 available to keep this propagation going. So we abstract a carbon-hydrogen atom from the substrate, from ethane in this case. Primary radical, that's the only radical we can get. So that's our intermediate from the first propagation. Here's our product, HCl that's formed. And then what? More of the ethyl radical adds to more of the chlorine, the molecular chlorine, and gives the halogenated product. And then the chlorine atom, you see, is the product, but it's also the starting material for this first propagation step. So these 2 steps are coupled together, and they'll go what? Until the material just winds down and gives you the product. Now you can have some termination steps. Let me show you that. Bring it back down here, Isaac. So we could have 2 chlorines coming together and go back to molecular chlorine. That's a redundant reaction. Of course, that can be activated right back to more of the halogen. You could also have this. You could have two ethyl radicals and form some butane. And there is a little bit of butane formed in this reaction, so that could actually occur. The other one that could occur is ethyl radical plus chlorine, right? But that's just giving you the main product. But all of these are low probability events. Why? These are all minor, very slow reactions. Why is that? Because the relative concentrations of these intermediates are very low. Okay, so the probability of the two coming together, high energy wise, is very low that way. We call these termination steps. So this will terminate. These all give neutral products, which are closed shell species, all 8 electron species. So these are stable that way, and it terminates the chain process. Okay, but this one can at least be reactivated and go back and form. Well, once this forms, yeah, you could start to halogenate the butane, I guess. But that's only formed in trace amounts, so you don't need to worry about that. And then this one here is the product anyway. So yeah, termination steps, I wanted to point that out. All right, let's get back to showing some selectivity reactions here on the board. Isaac, yeah, so leave it down here. Let's look at some other reactions and what type of selectivities we get from chlorination will be first. And then we'll do bromination, and we'll say something about the relative selectivities of these. So chlorine, light, and room temperature are key. So include those conditions, you know, if you want to do what? Monochlorination. So we'll form some of this, and we'll form what? Some of this. These are the only two products. The secondary and the primary spots. There's two of them, but they're one's coming from what? The secondary radical, one's coming from the primary radical. This one's formed 72% of the mixture. This is 28% of the total product. So that's not the isolate yield, but that's the ratio, you could say, of those two isomeric products. So yeah, they're constitutional isomers of each other, different ones. The secondary one is dominant there. What about this? I think I already showed this one. So same conditions here. What are we going to get? Chloride, secondary, chloride, primary. And what's our ratio here? Oh, 55% and 45%. So for chlorine, you know, you're always going to get a mixture of this. But what you can begin to see here is here you've got what? 2, 4 carbon hydrogens at the secondary spots, and you have 6 primary. So 4 to 6. So there's a relative tendency to form that secondary radical selectively, but not too much. The primary one still forms a lot. But look, now you've got what? 2 to 6. You've got a lot more primary positions. So look, the secondary one is less selective. And this is this relative selectivity issue that we need to get up here. So these relative selectivities reflect the relative rates of how fast these guys are forming. Let's do a more complex one here and see what we get here for monochlorination. So we've got a terp-butyl group here, an isopropyl group, and a methylene in the middle there. Oh, this is isooctane. This is the octane booster. They blend with gasoline. So this has an octane rating of 100. We talked about that. It's highly branched. It has a smaller surface area. So yeah, weaker intermolecular forces. So yeah, a lower boiling point. And it can be halogenated, of course. Chlorine, room temperature, and light. So let's go ahead and do this reaction. What do we get? Primary chlorination. And all 3 of those on that side are the same. We get some of that, 35%. We get some of this. We've got the secondary spot here, chlorinated. That's 26%. And we've got this one here, tertiary position, 17%. And we've got one more. Oh, we've got this guy. Also the primary position, that's 22%. I think those add up. I don't know. the relative amount. So you can see here, we've got a tertiary carbon, right? That will give a tertiary radical intermediate, and that is more stable than the secondary or the primaries. Notice the primaries over here are different than the primaries over there. So you get the 4 products, but look, the tertiary one does not dominate. It's 17% of the ratio. And that's because you've got 9 hydrogens over here. So look, you get more of this primary one, 35%. And there's 6 of these primaries, so that's quite a bit. Well, 22% is less. Statistically, you know, it's 6 to 9, you could say. And the secondary one, yeah, 26% is more stable there, but there's only one, well, 2 of them relative to the one tertiary carbon-hydrogen bond. So you can kind of see the selectivities wise there. There are ways to calculate this out, but let's just say chlorine radical selectivity. The relative ratios parallel the stabilities of the radicals, the carbon radicals, and the ability of chlorine radical to form those carbon radicals at that position. So we've got primary relative to secondary, relative to tertiary, and let's just leave it at this. This is normalized to 1. This is 3.8 times faster at the secondary positions, and at the tertiary positions, 5 times faster. You can actually use these relative rates here that we call these relative rates of how fast will form. Tertiary 5 times faster, secondary 4 times faster than primary. But it's weighted, you see here, for the number of carbon-hydrogen bonds we have at those positions. So you can relate it to that. Let's look at one other example here with chlorine, light and room temperature. And now we have all primary, but there's 9 of them, and then 1 tertiary spot. So we get a mixture again. We get this chloride plus the tertiary chloride. And what's our ratio here? Well, even though chlorine is 5 times faster, it's 9 to 1. So this one turns out to be the minor one at, what, 37% for the tertiary. And the primary one turns out to be 63%. Now, let's compare this one with bromine. This is the big difference. Let's just shine light on bromine in the presence of this alkane. Now, you might think, well, it's the same carbon-hydrogen bonds here. There's 9 of the primary, 1 of the tertiary. But if you look at the result here, it's 100% tertiary for bromination. Now, this relative rate thing here had to do with chlorination. What's the relative rate of bromination here? Primary, secondary, tertiary. It's quite a bit different. Let's see. What is it? Got the numbers again. Well, it's on your outline there. It's what? Primary is normalized to 1. Secondary, 82. 82 times faster, more probable if you have a choice between secondary and primary. And what is it for tertiary? 1,640. Okay, so it's primary to secondary to tertiary right there. Okay, so a lot more selective, we say, for bromine. And you can see here, when you have an alkane bromination now, with light room temperature, you're only doing monohalogenation, so you always just look for the most substituted carbon where you have a hydrogen. You still have to have a hydrogen. You can't do it at a quaternary carbon. So tertiary over secondary over primary. If you have secondary and primary only, then you only go for the secondary then, but 100% for that. Now, it's not just carbon radical relative stabilities, right? Because the carbon radicals are the same thing. But in that propagation step, you have also what the halogen halide bond energy involved, right? So the propagation steps involve the halogens also. So it's not, these relative rate relations are obviously not just the relative rates of the carbon radicals. It has to do with the mechanism. And the key thing here is all of the propagation steps for chlorine are what? They're going to be exothermic. Okay, and we'll see, we'll go to the overheads in a second. All the propagation steps here for bromination are endothermic. And that turns out to be the key for the selectivity. It's not the carbon radical stability. Let's go up above here and see this. What have we got? We've got the, well, that's the same thing. We're looking at the propagation step here, and you see that individual step for chlorination of a thing. Yep, that's exothermic. Let's see the next propagation step. Yeah, that one's also exothermic. Okay. Mainly it's because the relative stability of the carbon-chlorine bond is more stable than the carbon-bromine bond, and the hydrogen-chlorine bond is more stable than a hydrogen-bromine bond. We'll see. But you see these two steps, the two propagation steps for chlorination are both exothermic. So here's what it looks like, right? So we're going downhill each time, and significantly so. These are very exothermic overall. It's over 20 kcals per mole. So we're going downhill here, even though it's a radical. Why are we going downhill to a lower point where we're forming a stable HCl bond? Okay, even though it's a primary radical, that's okay. It is exothermic. And then this one's even more exothermic. Here we're forming what? The carbon-chlorine bond and getting energy out of that, and then it propagates back. So these are the two propagation steps for chlorination. And notice they're both what? Exothermic. So if we apply Hammond's postulate, this transition state here resembles what? The starting material or the product? Well, it's closer in position-wise here on the y-axis to what? The starting material. So this transition state does not have a lot of the character of the radical intermediate. Okay, and that's part of the selectivity issue we'll get to with these later graphics here. Here's the deal with bromination. So here we're brominating propane, but notice we've got a primary radical, secondary radical, but each of these steps here are what now? Endothermic. We're not getting as much energy out of the HBr bond here. So these transition states, what? Because they're endothermic now, these transition states resemble the electronic character of these two intermediates. So this primary pathway would be higher in energy than the secondary pathway. Okay? So this is a subtle nuance to the mechanisms. Chlorinations tend to not be selective. They get mixtures of products. Whereas bromination, because the steps are endothermic, we can differentiate these two transition states better. The red one is a slower reaction then, and the blue one's a faster pathway, which leads to more of what? Secondary product. And let's compare those on here with chlorination. So same thing with the propyl substrate, and what, we're going downhill now because of the stability of the HCl bond. Okay, and what, these are exothermic. So these transition states are compressed more, and by Hammond's postulate, what, these transition states more resemble the starting materials, not these products. So the energy of the pathway is able to go over both barriers easily and give both products easily. Okay, so it's not these relative energies stability-wise here. It's the transition states being exothermic. This is actually called the selectivity principle, which is a corollary to the Hammond's postulate. Don't worry about it. The bottom line is, if you chlorinate, give a mixture of products. If you brominate, always give the most selective product. Okay, and I think that's the key thing here. So let's look at a couple other things on the chalkboard here, and then we're done for today. So let's brominate butane and remind you why this is important. So here's one of the things that makes the world go round, okay, petroleum. That's a multi-trillion-dollar a year industry, okay. Pumping petroleum out of the ground makes not only gasoline, but heating fuels, lubricating fuels, and a lot of other secondary products, specialty chemicals that go into materials for buildings, building materials, and also for pharmaceuticals, and a lot of other materials that we enjoy, cosmetics, and the list goes on, of course. Petroleum, we can heat this up, in the presence of a catalyst, a cracking catalyst, usually a zeolite heterogeneous catalyst. Pretty high energy stuff, a lot of energy. And one of the products is butane. 4-carbon species, of course. You can make a lot of butane from a barrel of oil if you have the right catalyst. Petroleum, of course, is very long chain hydrocarbons, and a lot of carbons bonded together, a lot of mixture of different hydrocarbons. These can be separated out by distillation, or like I said, you can crack these, it's called, with a special catalyst and heat. You can make the lower molecular weight hydrocarbons, okay? Alkanes typically. Some alkenes are formed as well. Those can be separated. But what we're talking about now is functionalizing a carbon-hydrogen bond, right? So instead of just burning this, why not make it into something more value added? Well, we can brominate it with light at room temperature. And that gives us selectivity. Yeah, we can chlorinate it, but we give a mixture of things and over-chlorination, whatever. With bromine, Br2 and light, keeping the temperature down, but initiating it with the light, getting the bromine-bromine bond to break, and going through the process here. What's our product? Right, it's going to be secondary bromide, and that's the only product. Okay, there's only a trace amount of the primary for bromine, less than a part per thousand. Okay, almost all of it. And what you need for a quiz or test is just show the more substituted bromine. Why is this important? Well, if that was the only reaction, you might scratch your head and say, well, who cares, right? But what can we do here? Well, we can specifically form alkenes from it, right? In those alkene reactions, now we have a very reactive functional group, and all those electrophilic H reactions, hydrohalogenation, well, that would just be going back. Halogenation, hydration, we can form alcohols, of course. We can form halohydrins and then epoxides. We can form a lot of different things, and that's just a few, the ones that we've shown you in that chapter. So this opens up the ability to form all sorts of products from that one reaction sequence, right? And of course, we can form the alcohols directly here from hydroxide. Yeah, we get a little elimination there, but that's what SN2, E2. We could also form carbon-nitrogen bonds, form all sorts of amines via the diazo, or we could form it directly from ammonia. Ammonia is kind of a pungent chemical to deal with. We can easily form the amine from the azide by reducing it. That's a reaction we haven't covered, but there's a number of things that can do there. But yeah, you can imagine many, many other things there being made there that have different properties and things that we can do there. One thing to look at here, we halogenate at this position. We do have a stereocenter, right? So we should say what? Both enantiomers can easily form because the intermediate's going to look like this. And the secondary radical is what? Flat. So in the second propagation step, the bromine, when it reacts with that, can either come on the top, right? Or it can come on the bottom. And that will give us what? A pair of what? Enantiomers, yeah. So we should say DL there. There are ways to control that with selective functionalization of carbon-hydrogen bonds. Those require specialized chiral catalysts to do that. There are some biological processes that take advantage of this kind of thing too with hydrocarbons. There are different bacteria that grow on alkanes, which are kind of interesting. They give oxygenated products like alcohols and ketones from these kind of things. So it's not just us in industry making these things, but this shows you how this opens up from petroleum, alkanes, hydrocarbons, and then synthesis can be combined to make a number of things. I think that's all we're going to cover today. We're going to skip section 9 on ozone. You can read about that. Different halogenated hydrocarbons, the fluorocarbons deplete the ozone layer. Read about that. The next time we're going to get into allylic halogenation. So stay tuned for the rest of this chapter. We'll see you next time. Very good.